All right, guys, in this section 10-3, the topic here is parametric equations, part 3. And so in this section, what we're going to be looking at is, this time we're going to be looking at the parameter is going to be an angle, right? The parameter is going to be an angle. So that third variable is going to end up being an angle measure. And so, as you can expect, if we're dealing with angle measure, then we have equations of the form of sine and cosine that come into play here. And so here's the first type of problem that we're going to be looking at. It says, write x equals 2 cosine of theta and y equals 4 sine of theta in rectangular form. So here are my parametric equations, one for x, one for y, and my parameter here is theta, the angle. Okay? So now, can we take these and turn them into a rectangular form with just one equation with x and y? So can we eliminate the angle as the parameter? All right? Okay, now, typically what we would do is we would take this x equation, solve it for the angle theta, take whatever we get and plug it in for the angle in the y equation, and that actually would work just fine here. However, because of the fact that we can now use the Pythagorean identity since we have sine and cosine, we're actually going to use that to write the equation quicker and in a different format. So here are the steps. So to eliminate the angular parameter theta, first solve the equations for cosine of theta and sine of theta. So like on this first one, if I wanted to solve this one for cosine of theta, I could divide both sides by 2 and have it pretty quickly. That becomes cosine of theta equals x over 2. And solve this one for sine of theta. By dividing by 4, it becomes sine of theta equals y over 4. Okay? And so now, instead of continuing to solve this to do the inverse cosine to both sides and solve for the angle itself and plug it back into the other equation, I can go ahead and get one equation in terms of x and y just by using the Pythagorean identity. All right, so that's a quicker way to come up with the equation, and it'll end up being in a more practical form, as you'll see here in just a moment. Okay, so I can now take this and use the Pythagorean identity and say cosine squared theta, which in this case, cosine of theta is equal to x over 2. So I'm going to go x over 2 squared. So I'm changing cosine theta to x over 2 plus, and I can change sine of theta to y over 4. And all that is going to be set equal now to 1. And so in that one step, I have now eliminated the angular parameter. And one more step to simplify will give me this, x squared over 2 squared is 4 plus y over 4 squared is 16. And that's equal to 1. Okay, so now, when we have an equation in this form, we've eliminated, whoops, need my squared here, eliminated the angular parameter. Now I have just one equation in terms of x and y. All right, so we have accomplished the task. But, okay, this should look familiar. Okay, so based on the unit that we've just completed, we should recognize this equation as that of an ellipse that's centered at the origin with vertices 0, 4, and 0, negative 4, and then co-vertices at 2, 0, and negative 2, 0, right? And so the graph is shown here. And so will we take a look at this and graph it with the parameter, with the way it was originally? If I put in 0 for theta, okay, then, so first of all, if we graph it in this format, we'll get this ellipse, right? But if we graphed it with the parametric form of the equations, then I can plug in various values of theta for the angle. Like, for example, if we plug in 0 for the angle, well, remember, the cosine of 0 is going to be 1. 1 times 2 is 2. Sine of 0 is 0 times 4 is 0. So the first point on this graph is going to be at 2, 0 when theta is equal to 0. And likewise, if we let the angle be pi over 2, then we would get this point, 0, 4, and so on all the way around. And remember, because of the periodic nature of the trig functions, then the further I go with theta, it's just going to go around and around the ellipse, right? So regardless of whether you graph it from this rectangular form or you graph it from the parametric form, you actually come up with the same graph, all right? And like I say, we should be able to recognize this form of the equation as the equation of an ellipse. All right, so a few more problems to practice here. Let's say that we start with this, and we want to write this in rectangular form. Okay, so again, the first step is to take each one of these equations and solve it in terms of cosine theta, sine theta. So here, if I divide both sides by 5, I'll have cosine theta is equal to x over 5. And if I divide both sides by 6, we'll get sine of theta is equal to y over 6. All right, so then from here, I can plug into the Pythagorean identity, which will give me x plus 5 squared plus y over 6 squared is equal to 1. I can square that out now and get x squared over 25 plus y squared over 36 is equal to 1. Okay, so in this particular one, we're just asked to write it in rectangular form, but if we were asked to graph it, then we could recognize this as an ellipse. We could get our A and B and then put in the vertices and then go from there. All right, what about this one? So let's say I wanted to solve this one for sine of theta. And so that would be sine of theta is equal to x over 10, and the cosine of theta on the second equation is going to be equal to y over 9. Okay, so I can take these now and plug them in, and it would look like this. X plus 10 squared plus y over 9 squared equals 1. Squaring it out, we get x squared over 100 plus y squared over 81 equals to 1. All right? And so that's how we can eliminate an angular parameter.